Hello everyone. Today I wanted to continue our discussion about sharding, and this time I wanted to talk about a pure proof of work sharded system. And this paper, the method is called a monoxide. It's the title is Scale Out Blockchain with Asynchronous Consensus Zones. And this is by authors Wang and Wang at NSDI. I think it was 2019. Right, so this is the title of the paper. So let's think about it for a moment. So it's sort of a natural idea to think of that if Bitcoin is proof of work based, can we just have something like that replicated many number of times? Okay, so the idea is that you have let's say several of these. So 2 to the k chains, shards. Right, and can you do proof of work in all of them? So we might think, how would we do it? So suppose you just have one idea is you have let's say different miners working on different shards. Let's say a miner set 1 and then set 2 and so on. Okay. And each of them is doing proof of work over here, and they are creating blocks. So there are various issues. So first of all, these blocks don't come at a fixed time interval. Each of them is like a Poisson process. Plus you may also have forks. Some blocks may get orphaned and so on. Right? And if you're going to divide the hashing power among these various shards, each shard gets less hashing power. Let's say 1 over 2 to the power of k of total hashing power. So this is a problem. It makes an attack, a double spend attack on any one chain easier, because if the attacker can concentrate all his hashing power on just one chain, then he has to only beat 1 over 2 to the power of k of the total hashing power. It's not the total honest hashing power. Right? This is one issue, and also the issue is when you have things like forks, how are you going to do a cross shard transaction? So this is, I should say, one major issue. So here is an issue. So suppose somebody is paying money, let's say from this shard to the next one. The question is, when does this shard accept that that shard has debited the money? Because a block can be removed at any time, right? There is some small probability that a particular block is removed. So there is no such thing as a 100% final commitment in a proof of work blockchain. Whereas in this sort of sharded system, you would normally expect somebody's money to be first debited here and only then credited here, right? That sort of should happen atomically. But that's not happening over here, right? So the other papers we looked at, like rapid chain, we didn't use POW to actually generate these blocks. We used some sort of a BFT protocol, and we assumed that there were no forks over there, right? Whereas here we are going back to the old proof of work scheme, and we want to do proof of work everywhere, but then we run into these problems, right? So this whole thing of debit and credit from one shard to the next, if this is not final, then how can you credit to the other place, right? So these are some of the issues the authors wanted to address in their paper. Okay. So how should we go about doing this? So first of all, what sort of model to use for transaction? So the UTXO versus the account based, and this is used in Bitcoin, and this is of course used in Ethereum. And Monoxide folks say that they are going with this one. Right, so it's account based. So essentially, let's say your public key has, your account is, let's say, denoted by your public key, and it just what the state represents, it says what balance is there in your account, right? And the thing is that these two models are quite different. So here the advantage is that the entire state is stored on the blockchain itself, right? The UTXO is there on the blockchain. So Satoshi's innovative idea had that. Here a lot of information has to be stored off the blockchain, but still maybe a transaction might get into the blockchain, in one case, whereas it may not get into it in another case, right? So the models are a bit different. So suppose in Bitcoin I have two UTXOs, let's say, with the same public key. Right, and let's say that the total amount is let's say 2 Bitcoin, let's say one BTC in each of them, and I generate a transaction which spends, let's say, 0.5 from this. Right, and there may be multiple outputs. This is what I would do in Bitcoin, right? So the thing is, suppose another transaction gets in before this one, which has already spent, let's say, any amount from this UTXO, then this transaction would not get in, because this particular output from this transaction is no longer a UTXO, right? Whereas in an account based case, I don't have to worry about anything like this, because the money is not taking from a UTXO. I could have deposited in the account in many transactions. Let's say the account based model. In one transaction, let's say I do +1 BTC to a particular public key, and in another transaction I do to the same public key. So the total is, it's just that the state is stored as there is 2 BTC to this public key, right? And there's no such thing as this UTXO, that if I take a little bit from this UTXO, then that's that's the end of it. I can't reuse the same output of the transaction again, right? Here the spending has nothing exactly to do with these particular transactions. You just look at the total amount, and I can have a transaction which spends, let's say, 0.5 from this. Okay, it's not particularly linked to any particular transaction which put money over here, right? So there's a decoupling, and I could have spent a little bit besides this amount even earlier here before this transaction gets in. That's not an issue, because as long as you have more than 0.5, you can spend from this, right? So there are fundamental differences between these two. This is good in the sense that the entire state is on the blockchain. Here you have to maintain something off the chain, but there is also some flexibility that here, once you use a particular UTXO, then it's no longer a UTXO, it's done for, right? Whereas here there is no such thing. I can just incrementally spend a little bit, 0.001 even. I can do that 100 times, and that's still going to work out fine, right? I don't have to have new UTXOs and then use from those UTXOs and so on. Okay, but so there's a discussion in the paper about why they chose this. So they went for an account-based system eventually. Okay. So let's think about one issue. How do you do a cross-shard transaction? Some of the details of Monoxide. So first of all, blocks are structured somewhat like Bitcoin. So you have transactions, and normally we would call this a header over here in Bitcoin, but they call it the chaining block. Which is like a header in Bitcoin. So this points to the other next previous, let's say, chaining block and so on, right? And the Merkle root is stored over here. And this they call the transaction block. So how is this going to be used? Well, we have multiple shards. So a full node in any shard has everything of the shard, has both the chaining blocks and the transactions. This is right of its own shard. plus it's going to have the chaining blocks of all shards. So the point here is that these are very small, the chaining blocks are small, and they don't require much computation or storage. So they are small, less computation is required for validation, and of course there are low storage requirements. Okay, so every full node in the network, even though it belongs to a particular shard, is going to have all the information of the headers, which they are calling chaining blocks, right? It has all that information, and this is going to help because any full node is going to get some information about other shards, but it doesn't have the ability to verify it directly because it doesn't have the transactions. But with the help of Merkle proofs, it can very easily check that a particular transaction belongs to another shard. Right? So suppose somebody sends a transaction to the Merkle proof, let's say for a transaction in this shard to a node over here in this shard. It's very easy to verify because it has the Merkle roots of all the chaining blocks over here. Okay? So let's see how we're going to do cross-shard transactions. So there, suppose a user broadcasts a transaction which looks like this. So this is just the notation they are using, and this rho stands for withdraw. So it's withdrawing from this is the payer, and it is this is a deposit, and this is the receiver or payee, address. Okay. And so which shards are these going to be in? So they say that shard of A is decided by the first, let's say, k bits of A's address. Okay. So there are 2 to the power of k shards, we said. And the first k bits are going to decide which shard this person is, right? And similarly B shard, and we are assuming that they belong to different shards, right? Okay, so what are we going to do? So this is first of all sent to miners of shards. So this is broadcast to miners of A shard. Okay, and so what's going to happen is this is going to enter some block, so now what would we do? Let's think intuitively. The transaction has gotten to the particular shard, so the withdrawal is tentatively at least has been taken care of. right? So the withdraw operation has one conformation, and that's good, but it may not be enough, because what if that block gets removed, right? Then we are going to be in trouble. Okay. But anyway, what is done is that so the miner sends a proof to miners of B shard. Okay, somebody, it could be the miner generating this block, or it could be anybody, even the particular payer, for example, can send a proof, right? And how do you send a proof? Well, it's a Merkle proof. So let's say somewhere here is the transaction, and we said that there is a Merkle tree, right? So what do you have to do? You can send this transaction, you can send this one, right? You can send various nodes. So these are all the ones which I've tick marked in this Merkle tree. They are the Merkle proof. Right? So you can send that proof, and of course the miners in the other shard have this chaining block, so they can verify that indeed this was in the block, right? So now what should they do, right? So so they can include a withdraw corresponding to this. Okay, so this is a proof, and this is sent as what is called a relay transaction. Okay, so the relay transaction is going to contain this information, right? It has the original transaction. So in the paper they say that they send a subset of this, some information. I think you would have to send whatever is included here, because it's part of the Merkle rule, right? And this other information. Okay, so it has more information than just this transaction, in fact. Fine. So now, what should the miners in B shard do? Right. So what they can do is they can miners in B shard include a withdraw transaction let's just say that they include and the notation that they give here is I withdraw some amount, right? And sorry, this is a deposit transaction. And they have some notation gamma here. I don't see it clearly explained. Anyway, so this is included. So there is a slight issue. So suppose this is A shard, and this is where the withdraw happened, and somewhere later in time, let's say the deposit took place. It was over here. So does that mean that the transaction has successfully completed? So has it been confirmed? And the answer is not really, because what if this withdrawal is removed, right? Really, what do we have to worry about? Should we worry about n confirmations here? Should we want 6 confirmations here? Do we want 6 confirmations here? So what do we really want? So there's no 100% guarantee that any of these blocks are going to be there, but that's true for anyway for Bitcoin. The question is, when should the receiver assume, the payee assume that he has got the money? So this is one question. And when should miners in B shard allow transactions to spend money from the deposit transaction? Okay, so these are two questions, and so really, when should the person assume that he has got the money, right? So the thing is, so definitely you want a withdraw to be confirmed enough times, then you're sort of sure that this money has been withdrawn, right? And these two, remember, these two are connected. It's I mean, there is no other way to collect the money from this. I mean, it's not that this money which has been withdrawn can be deposited anywhere else, right? It can't be deposited in a third shard or something, because these two transactions are indeed connected. There's no way to have a different deposit transaction other than this one, right? So eventually this deposit transaction is going to be there, right? So once so if the withdraw has n confirmations, whatever n, let's say, this payee is happy with, then sort of he's sure that he has got the money, right? Because this deposit is eventually, I mean, somewhere or the other it's going to get it, right? So when should the miners in B shard start spending this money, and suppose this deposit comes in right here at the same time as the withdraw, and there aren't enough confirmations, then we could end up in trouble if we start spending this money. And this withdraw the block in which the withdrawal gets removed from the chain, then we are going to be in trouble, because then we would have to roll back the state for all of these, right? And all the people who got money from this, all these transactions, there could be a tree of transactions all connected to this, then all of those will have to be rolled back. So that's going to be a problem. Okay. So ideally what you want to do is that you want to start spending from this only when the withdrawal has had enough confirmations, so that you can be sure that it will be there. Okay. And do you have to wait, suppose n confirmations for the withdrawal are over, do you have to wait for also end confirmations for the deposit? And the answer is not really, because you're spending in the same chain in which the deposit is, so that's not an issue. If the block in which the deposit is removed, in the block in which the deposit is there is removed, automatically the blocks after it also get removed, so you don't have to worry about those, right? So essentially what we want is that the withdraw has n confirmations. So what I meant over here is that B shard I should not allow, okay, I should say, or it includes transactions from which in which money in this deposit is spent on. Okay. So effectively you want something like n confirmations here. So you can of course include this deposit earlier, but you're advised not to allow spending from it. Right? Okay. So this is how we do cross-shard transactions over here. So this is a simple A pays B idea which they've explained in their main paper. But in the appendix and so on of the paper, they describe more complicated transactions. But essentially whatever they do has to be, you should be able to split up into two parts, something like a withdraw and something like a deposit, which can be done separately. Okay. So let's look at the other issue about dilution of mining power. So we are doing proof of work on each of these chains, and we said that each chain, so the naive approach is that each chain has 1 over 2 to the power of k of total hashing power. Let's say total honest hashing power. And this is a problem that it makes attacks on any shard easier. So what could be a possible solution for this, and what the authors suggest is something, they give it a Chinese name, Chuko-no mining. They don't explain what that means, but it probably has some meaning in Chinese related to what they are doing. Okay. So what they do is they allow a miner to mine on n chains simultaneously. So how is this going to be done? So it's something like a voting chains which we had, for example, in Prism. And of course Prism's paper came out after this one. Prism was published I think in 2020, if I'm correct. Or maybe I'm wrong, maybe it came out in 2019, same time as this. But anyway, this 2 for 1 sort of scheme or n for 1 scheme we have seen, it's been used for several years, right? So you can simultaneously mine multiple blocks, right? So here they allow a different type of block. Okay, so what you want is that you want to have multiple blocks being mined. So you have something called a block or a batch chaining block. Okay. And here what you have to do is you have to be able to mine on multiple blocks. So I think maybe even more, they've given some details over here, but really what you want to do is you want to suppose there are multiple shards like this. And this is a miner who wants to mine on all of these, right? So you want to create your blocks so let's right, but at the same time you want to embed these in something else so that you can do a single proof of work. Right, and you want to embed these let's say through a Mockle route into this header. Okay, and so he's calling this a block, a batch chaining block, right? And you do proof of work on this. Right? So how is it going to help? So suppose you succeed in doing proof of work, and what they propose is the same threshold as normal mining. Right, and so there is a nonce over here. So if the hash of this becomes less than the threshold, then I say that I have successfully mined different
Sorry,
blocks.
I'm having trouble with the connection.
So if I am successful in mining, then n blocks are created. Okay, so this is controversial. I don't think they have studied the security issues involved over here, because what they are doing is that they are amplifying the mining of this particular user. So instead of him mining on a single chain, he's effectively mining on n chains simultaneously, and he's going to be able to generate n blocks in one shot. Okay, so it's almost as if this particular miner who's doing this is mining on every chain. I mean, and he's not just mining on a single chain, right? So let's think about it for a moment. So what are the pros over here? So it's theoretically possible for full mining power to be there on all chains. but it doesn't have to be. So if a miner doesn't want to do this, he need not do it. So what would you do if you were a miner? Let's think about it. You can get n times the mining reward, right? If you're successful, instead of getting a mining reward in a single shard, you get the mining reward in n shards. Okay, and n can what is the choice of n? Well, if you're an honest miner, you need to include transactions in all the blocks, and so you have to maintain the state of all the shards, all these n shards. Okay, but if you don't want to maintain the state, you could in theory create empty blocks, but there is a danger over there because you might be mining on invalid blocks, because without the transactions you don't know if a block is valid or not. Okay, let's talk about some cons. So miners need to keep state of n shards, right? If miner does not keep state, it can mine empty blocks. And this is dangerous, right? Because it might mine on an invalid block. That is a block with invalid transactions. Right? So this can happen, and how do you specify this n? Well, that information is there in this header, right? So n, the starting shard number is there in the block itself. Okay, so this information is there in the block header, and so you can start from any shard. So there's 2 to the power of k of them. So if I draw this 0 and 2 to the power of k minus 1 shards, I can mine on any of these according to the method that they have given. Right, so you can say where I am starting. Right, so that information is over there, and you might think, if you were a miner, what would you do? So at least I would mine on all the shards, and being a rational miner, I would just mine empty blocks on any shards for which I didn't have information, right, and just take the longest chain. But that would be a bit dangerous, right? So that's one of the shortcomings over here. But the good thing is that you have the full hashing power on all chains, and so that is going to mitigate any particular attack, any sort of double spend attack on any particular single shard. Okay. So we'd have to think what could the attacker do also. So the attacker might be able to do a double spend on multiple shards, right? I mean, you can do that. You can, but it's just that it would be, I'm just not sure whether it would be as easy or whether it would actually become harder. That's something to think about, right? So with this particular scheme, he can actually, let's say, I mean, of course, if it's a double spend, maybe the spend is only in a single shard. But I suppose he could also do a simultaneous double spend attack, where you have you try to do a double spend on n different chains at the same time, right? That's interesting, and maybe some of them would succeed and some would not, right? Yeah. Okay, so there may be other types of attacks possible which we would not have encountered in a single sharded system. Okay. So that's about how this Chukonu mining takes place. But the thing is, what do you broadcast out? So do you broadcast this entire thing when you're successful in mining? Well, the thing is, different shards may not be keeping track of other shards. So most of the miners may be doing single shard mining. So what this miner does is, he doesn't send all the blocks to everyone. He sends to any particular shard only the corresponding blocks, the corresponding transaction blocks, and a Merkle proof to this block chaining block, batch chaining block. So it sends to any shard among the n shards. So it's the batch chaining block, and a Merkle proof of transaction block for this shard. Okay. And so of course, I mean, you, in addition to just the transactions, you need to have maybe a chaining block. So let's just say that right. So there has to be information about which point, where you're pointing to, right? So in that paper, they just talk about a single hash of the previous chaining block, which is there in this. Okay, so maybe so you could include this chaining information also over here. Okay, but let's assume it's not there, right? But so let's say that we're doing the chaining. So this has the hash pointer to previous block in this shard. Okay. So all the information enough to create a block in this particular shard, but this you also need the POW proof which is there over here. Okay. So it's an interesting idea which they have proposed, but they haven't fully analyzed the security implications. Of course, NSDI is not really a security conference, so maybe they got away with it, right? But it's still a clever idea in which you can mine on multiple shards at the same time to make the system more robust, right? This is these are sort of the main ingredients of monoxide. So it's the Chukonu mining is one clever idea, and also the idea of splitting up a transaction into a withdraw part and a deposit part. That too was an interesting idea, and certain fine details had to be worked out appropriately, right? That you need N confirmation for the withdrawal in order for everything to work out properly.